Okay, good afternoon and good morning, everyone, and welcome to second day of Industry Day, German-Canadian Materials Acceleration Center. We do have one of our speakers and PI of the project in Canada. So I'm just going to hand it over to Mark in Canada to start and open the session. I'll come back with more information. Michael will follow with opening of our discussions, and then we take it from there. Mark, please.
Thanks very much, Courage. I'm Mark Cosras, and I'm an NRCan emeritus scientist and have been involved with the accelerated materials discovery since its inception back in 2017. And so it's a great pleasure to be part of the German-Canadian Materials Acceleration Center and the industry days that we're hosting, both yesterday in Canada and hosting in Germany today. I'm coming from Mississauga, our new facility for accelerated materials discovery. Go ahead for the next slide, please. Can the slide be advanced? Thanks very much. So in day one in Canada, yesterday, we had some interesting discussions. We were really learning about what maps are and how industry is deploying them. We also looked at how we work together and problems that are suited to accelerated materials discovery. It was happening through stimulus talks and panel discussion, and we wrapped up with some closing remarks. I'm going to deal with some closing remarks from yesterday at the end of today to talk about some of the things that we talked about. Today in Germany, we're hosting some things. We'll have this opening, we'll have a keynote talk, a panel discussion, paralleling some of the things, but we really want to get into more challenges and opportunities. So the integration of maps and accelerated materials discovery in the ecosystem under GCMAC. Next slide, please. So what is GCMAC? Really, what we're trying to do is harness R&D knowledge and infrastructure, and we'll see examples of that through today. We had some good examples of that yesterday to accelerate the energy materials pipeline and really take it from idea to innovation. And innovation means in devices, taking it through past materials to devices and systems. Thank you. How do we do that? Well, we support technology-focused materials research, and that's not uncommon. Our conventional science tells us to do materials research to advance goals against climate change. We, at the same time, advance method and tool development. You'll see a number of things that come up that say we need AI tools. We need good characterization tools. Those tools have to be integrated into systems that can actually solve problems autonomously or in an automated fashion. And really what we're trying to do is accelerate discovery, design, and integration of energy materials. We're very much focused on the hydrogen side of things, hydrogen fuel cell electrolyzers. And what we want to do is learn from all the different maps and accelerated materials platforms that are out there on different topics so that we can learn as much as we can, having come only in 5 years a long, long way. And one of the great pillars of GCMAC is to provide education and training programs. Examples are summer schools like the one that we'll be hosting in September later this year. Another thing that I'd like to point out is that Helmholtz International originally identified this as a topic of interest. And after we found that we didn't achieve funding through them, the Federal Ministry of Education and Research in Germany funded a project, a collaborative project in collaboration with Natural Resources Canada and the National Research Council of Canada as well. So that's where we came from. That's where we started. And I'll take the next slide, please. Some of the things that are really important, and we've seen really good examples of this yesterday, things like high performance computing. It's a complete enabler for the simulation and modeling that will inform the kinds of things that we're trying to do, the materials that we're trying to develop. We also have AI-enabled materials design. The aspect of AI is prolific in the autonomous platforms, these self-driving labs. We use it for experimental planning. We use it for big data analysis. We expect a lot of characterization information coming from the tools that we'll be using to characterize the materials and the devices along the way. And we need ways to fast process those materials. We always want AI to also accelerate the actual simulations. And so there's tools being developed around explicitly accelerating the computation and the modeling that we're doing. There's a host of other things that we're working on related to some of the hydrogen environment, and I'll talk about those in one of the next slides. You can see as well that a lot of activity is happening in Vancouver at the original site of Project Data, UBC, the University of Toronto, NRCan, NRC, and then over in Germany, we have Jülich, KIT, and Aachen University, who are closely involved in some of the activities. We're sharing different aspects according to our abilities, our capabilities in each of those locations. Next slide, please. So what is the workflow? What is the work package activity within GCMAC? Well, work package 1, really theory, modeling. The work package 3 is the AI-driven design and simulations that I talked about, how important they are to the activity in terms of getting the acceleration that we're looking for. Those are largely done in Germany. If you go to work package 2, the autonomous robots, we have autonomous robots operating in Vancouver, we have them in Mississauga, Hamilton, and we have them at the University of Toronto and Toronto. So the work package 2 activity is very active in Canada. Work package 4, focused activity around characterization, fabrication, happening at the University of Toronto. Again, a Canadian-centric aspect, and that's one of the things that we're offering to this package. Work package 5 is AI-enabled data handling and workflow optimization. So again, more about the data, how the data is processed, the data ontologies, the data curation. And so those are the packages that come together to create what we call the knowledge graphs and the data lakes. But what is a map really about? It's about predicting experiments, doing robotic operations, and then using computation to inform the AI so that we can move forward and develop new materials and or new processes. And it really hinges around expertise. One of the things that we did learn yesterday is that we want to free up our researchers to make sure that they're thinking and planning and setting the scope for the way that these maps could run. And so the associated experts are critical to the success of any autonomous or self-driving lab. And of course, it's built up from knowing that you can synthesize a material, fabricate it into a device, characterize both the material and device, and test thoroughly and get the test data out of the system. So that's what GCMAC is about. We're trying to pull together these different work packages to succeed on autonomous labs. Next slide, please. The areas of focus, and I talked a bit about the hydrogen file and the fuel cells related, the electrolyzer related stuff. That really is where we're digging into. And you can see challenge 1 and 2 deal with materials, the electrocatalysts themselves, the ionic media. We move into interfaces and electrodes. We expand to the importance of putting different materials together, how they perform together, and then up to porous transport media. We start to see that this stuff comes together to make a single device that might actually generate or produce hydrogen, etc. So we're moving to the materials, from the materials to the device, and that's part of the entire area of focus within GCMAC. Next slide, please. You can see the work packages are designed on the y-axis. You can see the work package 1, 2, 3, and how it creates a bit of a matrix from the materials challenges themselves. And so there's interactive activities between these things in varying degrees of work, but most of the pillars have an impact on each of the work packages themselves. And where we're trying to get from those work packages is to scaled up and integrated materials. We also want to go from the individual materials challenges to optimize terms for specific descriptors. What we're looking at is how do we get it converted from conventional output from characterization on these materials to something that can be used in a computational centric world. Next slide, please. One of the things that came up really early, and this is a great graph from Michael Eicherling, the co-PI for GCMAC from Germany. He devised a bit of a scheme to say, well, where are we in terms of applying AI-driven design and concepts on the x-axis? And then what are the socioeconomic impacts? Which ones will actually drive us to perhaps climate change and to economic prosperity? One of the reasons that governments fund these kinds of activities and accelerated activities is because there's potential for economic prosperity from these. You can see a lot of the technologies that we're working on. And this is not perfect, and people will disagree where things fit, the importance, the size of the bubble, but it doesn't matter. It gives us a bit of a map to say, what are the kinds of things that we could be working on that would actually be useful and helpful from an AI-driven design concept. And so it's just more to provoke people to think about where it fits within their specific activity. Next slide, please. The closing the loop concept is one of the things that is critically important for accelerated materials discovery. If you think of the current paradigm, the conventional science approach, we go through and we're developing, we get an idea, we synthesize a material. We talk to some people that they say they synthesize 2 to 3 variants of a material per year. And it really struck us as important. We need to be able to accelerate that kind of activity. The device construction takes further time. The testing and characterization, we move samples from lab to lab to lab where the equipment is, and that paradigm has to shift. Closing the loop allows us to predict and screen materials that we want to work on, then put a smaller set of materials into a loop that allows us to synthesize, characterize, learn, and then repredict the next experimental plan. And some of the things that we do is we look at massive experimental spaces. We learned that yesterday in the talks that came up. But it has to be emphasized that we're trying to look at experimental space that we wouldn't normally tackle in a conventional science manner. Next slide, please. What are maps? Well, I think that I've described it fairly well. We definitely have the AI core that we build up on. We have computation and the robotic automation, which is very, very important, and then closing the loop. The human in the loop, and it's one of the important things, that expert in the loop guiding the design of the initial campaigns, these large experimental spaces, is critically important. So we're not taking the human out of the loop, we're putting the human in the loop to constrain the robotic platform to function at its peak. Next slide, please. If you look at some of the conventional approaches to things, we might do modeling in one lab, prototyping in another, some autonomous test rigs. Maybe there's some high throughput characterization and synthesis happening, but it's largely done in individual labs. When we move to the model that we're looking at, we're collecting and connecting all of this. And it's really important that we have means to deal with that. Next slide, please. I think we're moving to the next slides. Courage.
I think that's at this point. Thanks, Mark. Michael is going to continue on focusing on the theme of the discussions today. So thanks. I handed it to Michael, so he's going to continue.
Sounds great.
Thank you, Mark.
Great. Thank you very much, Mark, for your introductory remarks and for going through these overview slides and presenting very well what is the scope and what are the activities within GCMAC. And so I will continue the story. At the last slide already introduced one aspect of the discussion that we're going to have today about integration. And that was looking at lab-to-lab integration, basically. Labs with different capabilities, with different instrumentation, different analytical abilities. must be integrated and must be coordinated to basically draw the best possible value out of that existing infrastructure. There are different aspects to that integration theme. So scale to scale, component to component integration. What I always liked very much about the field of electrochemistry was that it has influences from many different areas. So there's fundamental physics, there's chemistry, of course, there's material science, there's a lot of engineering. And each of these is very essential to the developments that we have to make in the hydrogen technologies, other technologies like energy storage and batteries and so on. So this is basically what we have to contribute to. So we have on the right-hand side, the technologies that are specified as being of importance for this energy transition that we want to help getting accomplished in a reasonable time frame. So there's battery energy storage, there's hydrogen for mobility and many other application areas, of course. There's chemical energy storage using feedstocks from the atmosphere, carbon dioxide, for instance. And so the developers of such technologies can tell us very well what are the requirements. And the users as well have certain expectations in terms of performance, cost, of course, stability, lifetime, and so on. Now that can be translated as well as we can to the material scientist, who then has an ability to apply certain of these properties into materials at a very fundamental level. So a materials chemist might be able to control the catalytic activity of certain compounds, of some complex structure maybe. If let's say there's an interest in moving away from the metallic catalysts, for instance, we need ionic media with good properties, and we need electronic media, so connecting different components in a system. So these functions might be very nicely designed into these materials, carefully done and tested and so on. Then, of course, we mess things up by putting them together, making interfaces, putting the interfaces into porous composite media. And the question is, of course, then what survives? What will remain after, let's say, going through these steps here of some scaling up of these nicely designed properties in the technologies? Will they be able to exhibit the stability increases that have been tested at, let's say, the XC2 scale in a chemistry laboratory at the university? Will that still be transparent? Will it still be relevant when we come to the technology scale? So the point is that, let's say, as we're moving along and scale things up from the smaller scale to larger scales and then getting to a device, we are picking up parameters. And so at each different level, there are different types of parameters that we can pick up. Of course, we cannot equally treat and be careful about considering each of the parameters that you can pick up here. Some parameters are more important than others, and so we may refer to them in a different way as descriptors. But we cannot have too many of those. We need a small number of descriptors. Now, let's say, again, back to the technology scale, there are the metrics of performance. And so if you're able to relate these descriptors to the metrics, then we have a sound basis for something like an AI-based design of materials. So that would be the basis for that. So now, that's basically the integration that needs to happen. Now I want to show you something, we have been dealing a lot with the fuel cells. And of course, one may analyze different technologies, for instance, perform an analysis for battery technologies, for the water electrolysis, and so on, whatever is in our interest. So we have a very good understanding of, let's say, what determines the mass activity. And we know that the mass activity is a very good metric for the performance of a fuel cell. So it tells us what is the current generated at a certain potential at a certain time. Let's say the fresh cell, the cell after some use, so that would be reflected in the time, divided by the initial loading of platinum. So this is cost. This is performance divided by cost, so that is a good descriptor. And we can, let's say, take a look how that has evolved over time. Over time scale of, let's say, more than 100 years. Invention of fuel cells goes back even further, but there was first practical cell around the 1890s. And then there was not a lot of development, not a lot of progress. There was a major breakthrough here. I will tell you later what that was. And from then on, the development has been very rapid. What people might not be aware of, there's kind of a 10 to 3, so 3 orders of magnitude increase in this metric. So, and all of this not achieved in, let's say, a very orchestrated way with a lot of involvement from the industry. No, all of this has been achieved with academic research, academically driven research supported with public funds. So imagine how much more rapid this might have been if the industry had that commercial interest in that technology from the beginning, as it had, for instance, in computing. So 10 to 3 increase. So what has driven that? Well, you might think, so there's an issue with the electrocatalyst material, because the electrocatalysis is what we must accelerate, right? So that has to get better with less platinum. Platinum is a major cost issue. But actually none of this has been due to the replacement of platinum, so achieved with platinum. And so the major breakthrough was that polymer electrolytes were introduced as the electrolyte medium. Membranes like a plastic bag with some ionic functionality in them, and so making these cells much more, let's say, giving them much higher performance. And then there's been some progress in catalyst layer design, so designing the media around the catalyst, not the catalyst itself. And then there's been some optimization of nanostructures. Small is good because it gives, let's say, higher mass activity in this case, and some optimization of the engineering. So that has contributed. So the 10 to 3 increase, a variety of factors have contributed. Okay, so now we know this for the PEM fuel cell. Okay, now let's take a look. Let's move away from that to water electrolysis as another very important technology in the hydrogen economy. So what we need there, and what is widely, let's say, accepted as a major requirement to achieve viability of these technologies, is that we will be able to increase mass activity, in this case not the platinum, but the iridium-based catalyst materials by a factor, let's say, about 4. And I've indicated that here, maybe this is where we are currently, this is where we want to get, okay? If we have the same speed of developments as we had it for the fuel cell, we would end up somewhere here. So this is a parallel line to this one that we have here, okay? And when will it get us there? This 40 times reduction in platinum loading by the year 2050. Okay, if that were the perspective, I think we could stop doing what we are doing. It would be a better bet probably to go back to nuclear power plants, because then electrolysis would not make a big contribution to the energy transition. So this has to be achieved in a shorter time. And so that acceleration that is needed is indicated here. So we have to get, so I indicated that this was doubling every 6 years. It's an exponential law, as indicated here with the logarithmic scale, 3 orders of magnitude. So if we want to achieve this, we have to get faster, and we have to do this doubling every 2 years. So this is where the acceleration will be needed. And so that is basically, well, we have to see where that could come from. So maybe we have to continue with the iridium-based catalyst, and maybe we have to look at other ways to achieve performance increases. And they might come from these different areas that are indicated here. So that's something that we'll have to see, but everything here, we need to have it on the radar. So we cannot neglect, let's say, certain scales and just focus on one particular aspect. So it's the catalyst that is important, it's the ionomer material or media that are important, it's a design of complex electrodes that is important, integrating everything into a well-functioning cell and optimizing the engineering problem. So all of this has to come together. And also it's not, let's say, as indicated here, we can be very good at making better catalysts. Once we scale it up and make an MEA, some of these improvements will be lost. If you go from the MEA, like the functional unit that has already all the properties of a functioning cell, if you go to the stacks, so something that has, let's say, it's the end of the development of the technology, we might lose even further. So we have to be really good here, we have to be selective, and to retain some of these improvements when we get to the real technology scale. So back to the scope of the discussion that we are going to have today. The objectives that was put out and discussed by Mark already yesterday. So we want to connect, of course, the researchers involved in our network, academic researchers, research in the public domain at national labs in Canada at NRC, so the National Research Council, and NRCan, Natural Resources Canada, universities that are involved, connect them with companies in both countries, but also expand out from Canada and Germany to include other institutions in other countries in this. Generate awareness and create opportunities for collaboration around this common theme that we have, accelerated materials integration for energy applications, and see how we can, let's say, together develop strategic initiatives that broadly support this accelerated materials design in the industrial sectors that we have on our portfolio. And so here, framing the day, so I leave this up, you can read through. So of course, highlight early industry engagement in accelerated materials discovery, promote the concept of self-driving or autonomous labs for energy applications, understand industry interest and needs in accelerated materials discovery, promote awareness of opportunities for exchange, training, and collaboration, and identify emerging areas of interest for accelerated materials discovery. So these are some of the questions, some of the discussion points that will be addressed later on, the discussion that we are going to have. So with that, I would hand over now to Florian Huber from HDE, so the High Throughput Experimentation Company. Just a few words about Florian. So he obtained his master's degree in 2002 from the University of Erlangen-Nuremberg. After that, he moved to Norway to obtain his PhD at NTNU in Trondheim. He stayed on and worked at Halle Topsoe for 5 years. And then he joined the company HDE in 2011 in various functions. And now I think he's leading the section for new technologies. And we are happy to have you here and looking forward to your presentation.
Let's see. Okay, so thank you very much for the introduction, and also thank you very much for the opportunity to give this key talk today. Yeah, High Throughput Experimentation Company, I guess the name is program. I mean, it's kind of, we talk about high throughput experimentation, but in the end, it's kind of part of this material acceleration platform. So it's just that we have a different wording. I will talk about what is driving us in this area, and especially focusing on new technologies we are looking at. So green hydrogen, electrolysis, and also battery materials. So just one or two slides for HE so that you get an idea where we come from. HE is subsidiary of BASF, but we are operating as an independent company with BASF as one customer among many others. We are focusing on catalysis and battery materials. We have a large high throughput experimentation laboratory in Heidelberg. We are slowly, all our business is coming out of Heidelberg, about 350 plus minus dedicated employees on this topic. And yeah, kind of 50 units in-house, more than 150 delivered. What are we doing actually? We have two pillars. One is like we are building high throughput experimentation or lab equipment for high throughput experimentation. We build it for customers who buy this equipment, use it in the laboratory, or as you see before, we build it for ourselves and do contract research in catalysis, materials R&D. So that are these kind of two pillars. So that also, if you buy things from us, then we have operated them ourselves, and we know how it works. So we typically say it's turnkey ready systems because we know that they work. The third pillar down there, kind of small, is the software part, which is essential for high throughput experimentation. In the early years, was only to service the hardware as well as the contract research. But over the last years, we see more and more interest in itself, so having an own selling point, and we'll see where this drives us. The areas where we are active, the classical one, the very classical one, heterogeneous catalysis, classical industry. And over the last years, however, we also realized that we also have the capability to look in different areas. One is battery materials, and the other thing is electrolysis. I will show you later why this one actually fits very well to us. So let's have a look at battery materials. I've just two case studies, battery materials and electrolysis, to give you an idea on how we think about high throughput experimentation on material acceleration platform. I have to say, we are private companies. That means we have to make a revenue, we have to make profit in order to finance our developments, our growth. Otherwise, I think BASF would shut us down if we are not profitable. So how do we think in battery materials? In general, our thinking always starts with workflows. Workflows you probably hear every day in our facilities. That's the starting point. And with battery materials, it's the same. Here's an example from cathode active materials, where we start at the synthesis part, then we go at the thermal treatment part, to the post-treatment part, and then to the cell testing. What is important principle for us is, of course, we need to have a high throughput. I need to say high throughput for us does not automatically always mean full automation. This is not the first thing we are talking about. It's always first look at the workflow, where are the bottlenecks and so on, and then we decide where automation makes sense for us. The background for that is also, in the end, everything we do has to be economically viable. It needs to pay off. We have to have a return on our investments. So important, of course, low cost of experiments, robustness of our technology. At the same time, flexibility and very important scalable unit operations. We are not doing academic research, but we are doing industrial research. So almost all our customers are coming from industry and have the corresponding focus. So if I just, let me just say here, so when we talk at this workflow, it's of course about a high throughput, meaning how many samples do I generate with each step, and how many samples do I have to treat afterwards. It's kind of a funnel, starts with a few samples, and since the parameters you can change, you want to investigate up road with each step. So therefore, typically the number also increases in that direction. The first thing is starts with, in this example, with synthesis, precipitation of active material. Here it's not necessarily about a very high degree of parallelization, so it's not about too many samples, it's more about scalability, meaning the samples that we produce need to have some industrial relevance. So that means they need to be comparable also when you go to industrial production. That's the most important part here. So but of course, automation, 24/7 operation is always, all our units are focusing on that. Analytics, of course, where needed. When you have prepared the samples, and typically the second step is now you go to thermal treatment. Then it starts the number of parameters. For example, temperature, atmosphere is increasing, which you can do with one single sample already. Here's just an example of what the temperature effect can do on crystal inside, which is important for later performance. So here we need to increase the degree of parallelization. So therefore we have this multiple furnace systems where we can take samples and calcine them, for example, at different temperatures at the same time. The third step then is number of samples increasing further, post-treatment of these samples. Here it's then really about full automation, parallelization, in order to really cope with all the samples and the parameters that increase further. And the fourth step is then when you go to the cell testing of the material. Here in the end, when we look at this cycle, in the end it's down here, it's the cycling, the number of channels that you have that will be the limiting part. And then in the end it's often an economic situation or economic point. How many channels do we want to afford? It's about 1,000 channels, it's about 1 million, plus minus. So, and then also how long do we want to cycle your systems? So here it's about when you go this way, you need to consider how many channels you have, how long your protocols are, and then you decide, you check what you can do in the single steps. And then you decide which of these steps maybe are critical in the workflow, and that's where we typically go into automation. As I said before, we typically do not start with full automation of this at the very beginning. Yeah, so that's kind of the thinking where we are in the battery field. Now, the second example is electrolysis. This is the of course, I mean, it's a very, we have heard it, it's a very important topic. We realized that we have to go into this topic because, let me just say, for the batteries, it was clearly the starting point was the asset for us, that's for sure. In this electrolysis field, we looked at that's a typical high throughput equipment what we build. It's very classic. You have like an electrical cabinet, you have like an analytic section, you have like gas liquid supply, you have it's a lab solution typically, so you have ventilation, you have sensors and so on. And the core thing, here you have the conversion unit. Let's call it conversion module. And what is our typical way? We use flow reactors, heterogeneous catalysis. That's kind of 20 years we're doing heterogeneous catalysis. We realized when you go to different conversion technologies like electrochemistry, where you have no tubes anymore, but cells. In the end, if you look from a generic point of view, the system that you need is more or less the same. Actually, we can take a lot of the stuff we have already learned here and what works well here. In the end, simplified spoken, we just have to exchange the core part of it. And that's kind of where we realize, actually, point one, it's fit to our technology platform. So it's not that we don't start at zero. We have our level, we have 20 years of experience with this kind. And so we have to add this part here. The second thing is very important for us, and the third thing with all the startup and all the announcement on what we need industry-wise, there is a lot of need for testing on the materials, as Michael just said. So that was kind of the motivation why we went in there. We had a good starting point, and it was an interesting field for us. So that's for the hardware part of it. Here's just a slide from Professor Eichel's group in Munich. They did an estimation for themselves, bringing them to the point that they realized they need high throughput equipment for testing. When you do this simple material testing, catalyst testing, you can do it in a simpler way. However, if you want to go on the cell level, component level, and also when you are now we are in the time where this technology is commercialized, is brought into operation. We learn a lot of stuff. We need to include long-term testing, long-term studies. We need to compare materials in the cell level. So that's one point. It's a number of variables that need to be tested, and also the duration is increased from just a few hours, maybe long-term test, 1,000 hour test. So when you have this in mind or in focus, then you realize what they did is like the electrochemical part is when you look at the experiments, the planning, the synthesis, testing, evaluation, that's by far the most repeated step from a timing point of view. So if you do it with single systems, it just takes too long time. So here it's really about going parallel and doing automation in order to really bring down this time. This is an example for a 16-fold unit. So that's kind of the motivation. You could also say that's a business case for buying such a unit in the end. This is how such a unit might look like. We are always, you have seen it in the intro slide, it's kind of, we are thinking modular. We have some certain modules that we combine to certain solutions, and then we have a customized solution. It's always more or less the same. The unit looks a little bit different as the other one, but from principle, from putting it together, it's more or less, it's always the same unit operation. And that's what I call modular construction kit here. And here it's an example where you see it's actually a 16-fold unit. However, it's modularized, meaning it has 4 modules, 1, 2, 3, 4. Some, again, analytics, gas liquid, here's some gas conditioning, electrical cabinet, but in the end, it's 4 of these modules with 4 cells each. and that can be combined in a flexible way. I said before, the infrastructure around it we know already. The electrochemical cell is not our core competence, so therefore we heard it yesterday. It's not always the best idea to reinvent the wheel again, but just to look for people who actually can do it already. Here we work together with Fraunhofer. We realized the cells on the market do not fit our purpose, so we had to do an own design, which is shown here. Again, as with the unit, with this one, it's also a modular system, so you actually, if I recall it correctly, you can operate 23 different electrolysis modes with this type of operation, so to give the flexibility. So that's kind of the hardware part of where we want to contribute to this high throughput experimentation of material acceleration platform. We are not with these units. We are not on the material screening only, but we are really on the cell level. A very important part for us is always this unit operate 24/7. So a critical part for us is software, the automation of this systems. And here it's again, we call it software workflow or data workflow. Very important for us that we can control the unit in an automated way. That's a very classical recipe editor for the programming. What was new for us, since electrochemical equipment was new for us going into this field, that we work together with Metron to actually integrate their software, the Nova software, into our software, so we can actually parameterize their software from ours. So as an operator, you just see our HD controls, the unit control software, and we are controlling the Nova software. So that makes it quite easy for handling. And an important, what I actually like a lot about electrochemistry is the analytics of electrochemistry. It's online analytics, so you can directly build it into the unit and can operate it on stream. I'm coming from the refinery area. We always had to deal with the oil samples. You couldn't do the analytics in the unit, so you had to take it out, you bring it to the laboratory, or you had a huge effort to automate this into the unit. And that's the nice part about electrochemistry. There is this electrochemical analytics, they can just be put into the unit. And that's a prerequisite. I put it here, that you actually can create an autonomous test rig, meaning that when you have the right ingredients like automation software for the unit, as well as a database, which I've not shown here. And if you combine these two, you can upload automatically data to the database. There you have automated scripts that do the calculation. Then you give them some target values, what you want to achieve, for example, for a certain constant operation. Then the database gives a message back to the unit. And then the unit is adjusted, for example, temperature, flow rates, whatever, in order to meet this target level. So this is this kind of automated feedback loops, what you can do if you have online or inline analytics available. And that's really a nice part, because then the unit really runs 24/7, and within some, let's say, safety limits, which you give, you do not have to interfere. The unit is just operating on its own. And that's what is very important for us, because then you can really do long-term testing without having monitoring in the night, in the weekend, very practical problems if you have this online available analytics. So very important is software workflow. Without software, without data, without the proper data workflow, no high throughput experimentation properly. So yeah, that's kind of described here. If you talk to us, yeah, I said it before, we're always talking about this workflow. I also said it, we have two software packages, the unit controls, the database, and they work together. And in this way, we can, within these two systems, do the planning, documenting synthesis, documenting the testing, also the analytics and data evaluation. Very important, this little sticker here, this barcode, that's actually I always say that's the most important part in the whole cycle here, because that keeps everything together. All the samples, it's extremely important. Without this one, you just lose track of the sample. The effort is high. So very important from our point of view. Now, finally, 2 slides where I looked a little bit over the last 20 years, what we have seen and what we, from our point of view, it's just our point of view, not more, not less. How we look at high throughput experimentation, or also this acceleration platform. The most important part is that the data are flowing in an efficient way, however you do it. And what we see is one size does not fit it all, especially if you are in the research part. Things might change, steps might change. So if you lock yourself in certain ways, that makes it difficult to really be flexible enough. So therefore, I had this concept of modularization, which gives us a degree of freedom to choose between just parallelization and flexibility in a customized fashion. So everyone gets his own solution. That's kind of, our units are similar, but typically they are not identical. But by doing this modularization, we can keep the effort low in this respect. Yeah, I said it, data workflow, very important for the data workflow. You need a good software. And if you have these two, you can actually go to this automated feedback loops, which bring you closer to autonomous testing systems. And all of our thinking starts with what we call workflow analysis. We are looking for the bottlenecks, and then we decide on the degree of automation, because there's always this economics behind our heads that yeah, needs to be also justified, return on investment and so on. If I would look at high throughput experimentation, I just define 3 levels. I think the first level is like this: we have some single cells, some single islands which are automated. The second is like the data workflow, and the third I would call artificial intelligence. So it's kind of first is this high throughput islands, then you have to connect the dots, and in the end you have to add intelligence to the system. And if I look at it, I would say what we see with our customers, it's just our view again, what we see, the industry as a whole is working on, the first level is more or less done. A lot of people have automated systems, but this connecting the dots, that's kind of consolidating on an average level, I would say. And then you have especially academia and also industrial front runners that are actually working on this third level. That I would just summarize where we are right now. And also for us, I mean, we are also, this is not the state of the art for us as well, but it's a very important topic for us as well. So, yeah, and therefore I think, yeah, we fit quite well into this thinking of material acceleration, and especially the topic where we actually bring intelligence into, artificial intelligence into Okay, so that's my view or company view on this topic. Yeah.
Thank you very much, Florian. Very nice perspective and stimulus for the further discussions that we are going to have. Florian is also part of the panel. But if there are some questions now that you would like to ask him, you can take it.
In terms of acceleration, that you can accelerate along the characterization part. You show the slide the materials on and it follows this part where you show that thanks to your high flow experimentation, you can shorten a lot the time of development. If I'm not mistaken, when you show the slide, there is not a shorten of the period of the synthesis.
Yes, that would be, I didn't say that. When you have managed the biggest portion, the next step is certainly the synthesis, and some people are focusing on the synthesis. from our point of view, I would say from where we come from, and also since, especially when you want to go to long-term testing, this is really the bottleneck, as I said. But if you have solved this one, then of course you would look to the next part, and that's clearly synthesis as well, because a machine that is running needs to be fed with samples. So clearly automating synthesis is also a very important part.
In terms of shortening the time of the characterization, you, based on your experience, you can do this on, let me say, all the kind of characterization or more focused on the electrochemical. Again, for example, as far as we know, one of the bottlenecks nowadays that is really difficult to solve is when you have to characterize from the chemical physical point of the material. So if you have to do the phase composition or the chemical composition. So when you show characterization, you show electrochemical characterization, if I'm not. You also able to shorten the time of other kind of characterization, or is it something that you don't want?
I mean, our focus is clearly the electrochemical testing. Yeah, I mean, there you could actually add on then, because when I say that, I just said like, okay, now you can shorten or you can speed up, not shorten, but speed up, for example, in the example 1,000-hour tests. The next topic would then be how about accelerated testing, because you could shorten even further, which is a very important topic, and which I think is established very well in the classical heterogeneous catalysis field. I would say not that good in the electrochemical field. But here, if you want to do it properly, you need to have proper protocols. Everyone can accelerate aging, but the question is always, is it realistic and industrially relevant? That's the important point. And therefore, I think you need to do some effort to really do proper testing protocols with industrial benchmarks. And here it's a little problem also with the electrochemical field. These benchmarks are not so widely available as, for example, in a refinery, where they do it since decades, and where you know very well what is your reference point. And I always stress the most important thing about this accelerated aging is that you have a well-defined reference point, which is your benchmark for the protocol development. Very important. Otherwise, it's just stupid experiments.
Okay, so yeah, that's already very well going into the discussion. But one more question, and then we move on.
Sorry, we have a question over here on Zoom. I don't know if you can hear us.
Yeah, we'll come to that then.
Yeah, we'll
Yes,
come to that.
yes. One more question here, and then we come to you. Okay.
Okay.
Yeah.
Thanks. I would be interested in the reactor size that you use and the amount of parallelization that you deploy and setup. So what is the volume?
Typically, that's changeable. We can go from 1 square centimeter to 20. So it really depends on, and then that's our cell. However, we are not limited to our cell. We also incorporate kind of short stacks, and then you don't have like single cells, but you just take a stack and there you just ramp it up. So that's the point. We are actually not the one who focuses too much on a certain cell. We are system integrator. So we, if necessary, we take the cell of our customer. We have seen that we need to have an own cell, but we are very flexible on that. But our classical size is up to 20 centimeter.
Thank you very much. Anjali, please.
Yes, so a question here on the side from Yogesh Sharma from IIT Roorkee.
Should I come here?
They can hear you, yeah.
Okay. Actually, yeah. I just wanted to know about the total time to take for test a battery material starting from the synthesis. A new material, if you start, how much time it will take total to test a material as in a coin cell format?
At the moment where we have no full automation of the whole workflow, it's typical, and we are also, I would say, limited in the channels. We typically, the speed that we have given us at the moment is 1,000 tel per 2 weeks, because that's a time period which we typically use for the testing cycle.
Okay, thank you.
Is there any other question from Hamilton or?
Yeah,
is there...
one more question.
Yes.
Yes, it's Mark Cosgris. Florian, thanks so much for the presentation. It was very informative. My question revolves around your interaction with Metro. You commented that you were able to get the software and integrate it into your control system, which is extremely advantageous. I was wondering, can you comment on the general approach and the amount of effort it took to be able to get them to agree to have that common language that might be proprietary to them? Can you comment around some of that? Because we're going to have to see that a lot in the future.
I mean, in the end, we are not going into their software, but it's a classical topic that you define interfaces. So they define their interface, we define our interface, and we had to program, I think, about 2,000 lines of code, and then we were done. But of course, here we are again at yesterday's discussion. Therefore, you need a good cooperation. It needs to be a win-win situation. And I think we could establish with Metron that cooperation. And in the end, it's really about interfaces. We heard it in the materials have an interface topic, but I hope I could show it. Also, the software workflow has an interface topic as well, because we have very well developed software packages for these islands, as I said it. But the topic of connecting the islands, it's also a software topic, an interface topic. Yeah.
So, okay, we would end it at this point, but there's a question by one PhD student, of course, that is one that we have to take, please.
Yes, thank you very much for the talk. I have a question regarding automation, because you said that you're a company and that economics are very important for you, and that your first priority is always to have a high throughput experimentation. But how do you decide or benchmark when it's useful to really automate and why not? Because I thought that you said that you modularize very well, and then I would imagine that I would say that the costs to automate are always very similar, right?
Yeah, I mean, the point is always, especially when you start things, the first thing you don't do, I would, at least from my point of view, there are certainly different points, but we typically start not with a full automation because we need to ramp up things, point one. And we also typically, one point is we need to find the right workflow, which tools we need. And the second point, we are service providers. That means people are doing it in different ways. So we need to have a certain flexibility. And that are these kind of ingredients why so I would maybe from the logic secondary topics, but that decide on that we say maybe we are not ready for automation. Maybe the business does not allow high degree of automation because we haven't the numbers yet, we haven't the number of projects yet, and we need to ramp up first. So these are these kind of considerations actually. And in the end, yeah, I mean, automation is some effort still. And sometimes actually, especially in the battery workflow, if you organize it very well, you can actually do a lot also with just organizational topics and removing bottlenecks. And that's where we are, for example, now. So some parts are automated, others are not. But it needs to fit together. You need to look at the numbers.
Okay, well, thank you very much. So let's conclude at this point and bring in all the other panel members into the discussion so that we will continue. Of course, please.
Yep. Thank you. Thank you, everyone, for the discussions. I'm pleased to introduce our panel members today, very distinguished panels, diverse type of industry and focus, and I'm sure that will add a lot into the conversations and discussions that we just started after Florian's talk. So I'm pleased to introduce them one by one, and welcome to join our panel as I introduce you. Dr. Jens Hausch from Higher, another institute in Jülich. Jens is heading the research unit in Higher, very much involved into automation. And please join us. Mr. Michael Felder from Zinser, highly involved in automation, manufacturing of the customized equipments. He's manager at the company, and we very pleased to have him as well. From ECI, from EIC, European Innovation Council, we have Dr. Matucci from EIC. Francesco is involved in projects as project manager in Innovation Council. Thank you. I want to make sure Michael is online. Dr. Paul from Expo Fuel Cell. If you can hear us.
I'm here, yes.
Okay, great. So Michael also joining us online. So we have 4 panel members in person, and then we have Michael joining us online. He's heading development of component fuel cell in Expo Fuel Cell, and contact of all these panel members are there. If you want to contact him afterward, of course, his own. And then Florian, I think, introduced himself enough in terms of the focus of the HDE and the company. Yeah. Okay, I'm just going to start a little bit of how we're going to do the panel discussion today. We have sort of two sections here that just want to make sure we have this right here. So we want a little bit at the end. So we're going to start a little bit with introduction of the panel members and their sort of focus. We have 2 questions that are very specific to sort of general understanding of the impact of the acceleration in an overall view. We ask the same questions from audience online and in person as well. Once it's finished, we go a little bit more into the deep discussions of the specifics, into the clean energy materials, all the aspects that was discussed, and we'll see how the discussions will go. So without further ado, if that's okay, I'm going to start with our panel members who is online. Just make sure we get his view and the introduction to the company as well as his focus, and then we take it from there. So Mike.
Okay, great.
Can
you hear me? Okay.
Yes, fine.
Okay, thank you. Thank you everyone for having me. It's an honor to be a part of this discussion. My name is Michael Paul. I am at the company EKPO Fuel Cell Technologies. I am the head of advanced development cell component. So I guess I'll go through my slides. It's easier format. I actually I'm Canadian, so part of the reason I guess I'm here. I'm Canadian, originally from Vancouver. I got most of my degrees in Simon Fraser University, and then I moved to Germany and actually joined also Forschungszentrum the Helmholtz Institute in Nuremberg. Throughout my academic careers, I have been participating in a lot of different projects with the industries. From I think I hold one and MITAX on the work, so 1 CRD grant, and then I have multiple Engage and Engage Plus grant with different companies, but then all in the sector of clean energy. So electrolyzers, I guess there was zinc air fuel cells, and then of course PEM fuel cells. So at EKPO is a stack developer. We deliver a very high power density stack as a final product. So we're one of the few big ones in the world. We have a very high power of 6.2 kilowatts per liter. I am responsible for a team of scientists at EKPO that we do the development, verification, and validation of the components for the product. So essentially we're the R&D, and then we tell the engineering group what's okay to use. So upwards from catalyst to membrane, GDL, bipolar plate coating, subgaskets, sealing materials, and all that needs to be validated, and then also needs to be developed and then also validated from my team. But then of course we're always looking for innovation. So in my team, we're also involved in a lot of innovation projects. We're a lot involved in EU projects and also the BMVE projects. And I think we are also submitted 2 times the NIC project. And then recently we had just one, just also went through for the NIC fund. So we're always playing a balance between, say, innovation, but then the product needs to be at a sufficient APQP level, I guess APQP level or TRL level to be able to go in the product without problem. So for more information, I guess we did actually have a paper out with actually in collaboration with NRC on the review of the function and attributes of the materials for fuel cells. So for example, you look at the graph on the right side, that's the basic property of a GDL. So to properly specify a GDL for automotive applications, you have to be very careful about all the parameters around the GDL. So thickness, conductivity, thermal conductivity, electrical conductivity, and then one needs to validate these properties within a given range. And then we need to specify this range with the suppliers so we can ensure that it's a good product going into our final assembly. So for example, you see this is our NN12 twin stack. It has 598 cell and maximum of 225 kilowatts. And then in our NN12 system, you see the picture on the right. There is almost 600 cells, meaning there's 1,200 pieces of GDL. There is catalyst on both sides, and there's 600 cells of membranes. If you have a good rate of 99.9%, you still have you still have close to 10 dead cells in the stack, and then that's not acceptable in the production. So in our validation process, we really need a really good process, but at the same time keeping in mind the quality, the innovation of the materials. Yes, I think that's all. Thank you.
Thank you, Mike. Thanks for that introduction. Let's move directly to Jens. Introduction of activities in the center.
Yeah, actually, you can show everything. I forgot to remove the animation parts. So my name is Jens Hauch. I'm a head of the research unit, high throughput methods and photovoltaics at the Helmholtz Institute Erlangen-Nuremberg as well. And I'm also, we recently won a large-scale grant from the Helmholtz Society for creating a technology acceleration platform that is about transfer activities with industry, and where we're really trying to go from this idea of a materials acceleration platform to getting all the way to a technology that is in the market and that is actually being sold out there. And that, of course, involves a lot more because you need industry players along the whole value chain in order to support you there. When we talk about high throughput methods and photovoltaics, what we are thinking about is that we are classical material scientists. What we develop is solar cells, photovoltaic cells. We have the classical know-how in semiconductor physics and analytical techniques that come from material science. And several years ago already, we started taking this domain knowledge that we have, and we wanted to put it together with modern methods that are more and more available. These are robotics, these are data methods, artificial intelligence. And we wanted to bring those two together. And back then, the materials acceleration platform word wasn't really known yet, but nowadays this is what you would call it. In our labs, what we have done is that we've automated a large amount of different laboratory techniques, starting all the way from synthesis, then creating solutions from materials, creating films out of these solutions. In the end, we want some solid state thin films. Our fruit fly, as you may call it, you see on the right side here. So that's a typical layer stack. We work with the solid state thin films in the end and put them together in order to create a functioning solar cell. Then we've automated the making of a full device, a characterization of the device, all the way up to then the actual aging of the device and figuring out what stability is. In the end, for us, as well as many other technologies, it's all about efficiency, about stability, and about cost. And we somehow need to optimize ourselves and our systems inside this magic triangle, as it's often called in photovoltaics.
We've gone further from that. So these are still individual processes. We've already heard about interfaces as a very important part. And what we wanted to get to, or where we're at this stage, is that we can take solutions, automatically make films and layer stacks from them, turn them into finished solar cells, characterize them, age them, and take all this data in order to then design an experiment to optimize in the next step, our next level of experiment. And to do this, we needed then, on top of this automation of individual tasks, the orchestration of many pieces of equipment that actually work together, that create data, and we needed to take this data and put it into a loop. And what we've done in the last couple of years is that we've actually closed the loop, and we've already discussed that today here too. So we can take output data once we have something, and we can feed it to a Bayesian optimizer, and the Bayesian optimizer will tell us the parameters for the next experiment that we want to do. And we've quickly discovered that it actually takes too long. You don't want to make a full device, age it, and then take the data and go through. So we've also added in other techniques that allow us to take parameters, descriptors, as Michael mentioned earlier, to predict the performance that we actually care about, efficiency and stability, early on before we are actually making a device. And this is this is a current activity that we're working on that we're actually going to publish relatively soon, is we can very early make a thin film. We can characterize it in a very fast measurement. And this is also something that we've learned. We need simple measurements. This is simply using UV vis absorption. From this, we can actually predict our key performance parameters for a solar cell rather well, not with a 100%, not exact to 100% precision, but reasonably good. And we can take these results very early in order to accelerate these feedback loops. Then we can still finish devices and take the final data and feed it back in order to then do even better predictions. And in that way, we can very efficiently and quickly optimize a typical thin film system. And currently we're doing this in 4 experimental dimensions, and we're increasing these dimensions. And it's really helping us to move faster. And in the next steps, what we really want to do is start integrating the synthesis and have sort of a two-sided feedback loop, one creating the materials, the other one optimizing the devices in order to make our way much faster into the final product. Thank you.
So next, Sensor Analytics. I am analytic. Michael, please.
Hello, everyone. I'm from a integrator company from Germany. We supply lab automation products since 1990, and we have a heritage of supplying chemist application-oriented automation products, as well as obviously in the last few years also biology-related products. And I see myself as a lab automation consultant. And we supply customers solutions in the for labs to carry out the initial synthesis in the corresponding field of yours. And we prepare the projects, but we are not really involved in the research on the materials on themselves. So my focus is here definitely only the engineering part, and that is my topic that I could give an input for today, and I could give similar, let's say, examples as my first 2 colleagues over here already gave.
Thank you. Thank you. We'll get back to all the aspects of what you mentioned and the information as well. And in the last introduction, but not the least, of course, by Francesco, please.
Thanks, Korosh, for having invited me. I'm Francesco Mattucci. I come from
Brussels. I work at the European Commission within this new agency. So here I represent the part of your taxes. We invest your taxes to use them properly, if possible. And we do this. The agency has been officially set up in April 2021. We provide to all the stages that Florian described before, also in terms of advanced materials. We provide funding to the deep tech solutions, where deep tech is something that comes out in a generic sense from a scientific discovery. And we do this for partnership as well as for small, medium enterprises. We provide funding via a grants, but also via equity, because the European Commission set up the first venture capitalist fund that is managed by our agency. And we do this from the very early stage. So from what you are, I think, all familiar with the TRL. So from the very early stage TRL up to the market. And we do this in a not so incredible way, because the Commission doesn't do a lot of incredible things, but we do this in what we like to call in the hands-on approach. That means we, as program managers, we are the in-house unit of our agency, and so we help and we identify in writing the challenges of our work program. Approximately, our agency has got a budget of in between 1 billion to 1.5 billion each year. And once we identify the challenges, we are part of the evaluation of the projects, of the proposals, and then we work with the proposals, trying to identify with them the best way to facilitate and to accelerate their bringing their ideas or their products or their whatever is the technology from the research lab up to the market. So this is, and obviously we work, I am responsible as program manager of advanced materials for energy and environmental sustainability.
Thank you, Francesco. So we're moving right away into a lot of aspects of the first two general questions that I think was addressed to a large degree. These two questions, including some format of introduction, is also open to all the audience. So if you want to contribute to this by the end of the discussion, feel free to scan this barcode or go to slido.com with that number 3612472. If you see it on the screen, I keep it for 3 seconds, or at least a minute here, so we can do that, and then renew all the questions one by one every 15-20 minutes, so we are able to basically answer that. So I'm going to reflect on what was discussed here originally. I think a lot of things on the first questions that determines the interest of the panel members from the perspective of the company in the acceleration materials discovery or the lab sort of requirements that the acceleration is required. So I want to get back to that question a little bit. In terms of the economic value, I think that's probably things we're going to look into. Either you are in the automation industry, you're not the end user of the acceleration, you're sort of enabler in a way that you're providing equipment. What really would be any other interest that we haven't addressed in your introduction or into the few questions that we had here? If that's okay, I'm going to start with Jens on that question, since we talk about in the next question about energy materials. I want to get into that interest from the automation from the lab, and then I want to hear more, of course, from the industry partners. Please, Jens.
So the first thing that comes to my mind that wasn't, I think a lot of issues have been addressed today. What hasn't been addressed from my point of view is transfer learning. So how do we actually, because nowadays we have solutions to automate labs, we have companies that can do it for us, we have solutions for databases or electronic lab notebooks that allow us to collect data efficiently. A large part that is missing for me now, though, is a structure that allows us to exchange data efficiently between many labs. So at the Helmholtz level, we are organizing activities between the Karlsruhe Institute of Technology, between the Helmholtz Center Berlin, Forschungszentrum Jülich, and we all sort of have our own data structures, but we haven't really managed to communicate very well, not even at the metadata level. We haven't been able to connect our data sets yet. And I think in that area, we need a lot of work and a lot of innovation. We need ontologies, we need standards to do this. And we need standardized systems that allow us to do this without everyone always having to invent something on their own. There are activities going on in Germany, but I think this is really a point where we're still lagging behind right now.
Yeah, so that's a great point on academic lab, or for the sake of technology development at the earliest stage, the needs for industry standard, or let's say standard best practice type of the data that is required for that. So I want to come back to Florian on that aspects is as you are focusing on a new area, obviously battery and electrolysis, as you mentioned, with your experience in heterogeneous catalysis in the oil industry. So how do you see the acceleration in general is important even for that industry? Is there any aspects of that that you think missing in your services that you provided to that industry that still you can go and leverage? In addition, of course, entering into battery and others. And the second, I want to follow up on that point on the data standard. And is that something that also industry is missing because you're interacting with clients, of course, on both end of data and development? Maybe you can elaborate on that a little bit more from your perspective.
Yeah, I mean, it was just said, and I would just strongly support that the topic of standardized protocols is a very important one, and especially since I'm coming from the refinery where we have this learning done already, working properly on aging and accelerated aging is a huge topic, because what I have learned is you can do a lot wrong if you don't do it right, and therefore I think there needs to be a focus on it, and especially what I see is I mean this especially if I look at electrolysis, for example. Now it's introduced now, it's kind of getting into the market, it's used for the first time. If I look at what we are doing in the classical area, we are developing new processes there as well. However, our main business there is optimization. Most of our projects are on optimization. So this wave is first coming once we have had the first generation in, and then really going for optimization of materials, of formulation, and so on. So that's this part. Yeah, data is certainly a topic. I indicated it a little bit on with this last slide. I think in academia, people are quite far already. What we see with our customer, the picture on data integration is politely said, very heterogeneous. You have very well developed companies, and you have others who actually are still missing the basics. So that's this having a homogenization on that part. That also is like with the data, that they need to be homogeneous, that they need to have a certain format. I just saw fair as a word for it. So that's clearly something that also hinders acceleration.
Yeah, we definitely come back to that point of harmonization in different aspects, in different technology. So Michael, you are obviously coming from as an enabler to this. You have technologies that basically make all these things possible. So again, back to our main questions, how this acceleration is helping your business in general. And also to the second question, that so materials innovation in general as one of sort of line of business for you, I guess. Would that be something that you have a specific perspective? Is it going to grow? That is a sort of a sector and vertical that you have a lot of hope to grow? And maybe you can elaborate on that from your perspective of the equipment manufacturing and customize as well.
Well, our most important topic as a GmbH and a shareholder company is to earn money. And obviously, the topic that we searched for doing that is to support scientists. And we have the tools to do that, and we just have to, let's say, search for opportunities to really use them in the market. So from our humble point of view, the chemist market is obviously one. Apart from that, we have had like a small crisis in the last 2 years, which was solved by a new phenomenon like the mRNA and encapsulation of mRNAs. This is a field in which like 50% of our revenue is purely sitting in. And we're supplying one of the larger vaccination companies here in Germany with products in this respective field. So I feel really safe that the field of synthesis may not only involve the synthesis of chemical components, but also we are sure that there's a growing market in the mRNA sector, and we are involved with that. So we are not also focusing on that. So that is our niche that we employ.
So is in terms of sort of other verticals beyond materials, what was your experience if you had more uptake on some other areas such as pharma or metallurgical materials and all that you think it can be replicated also into materials as acceleration as well? Is there any insight on that you can share as well?
Well, the technology modules and options, as my colleague Florian also told before, could be used for several applications. And so I have a personal opinion, if you share the corresponding options that you have with scientists and tell them about experiences that we made with them, give them ideas on how to employ the options, this can cause the use of, let's say, these options in other fields. As I mentioned, the mRNA field is just one of them. We are sometimes surprised in which fields these options could also be used. As a side note, for instance, also for chemical warfare research, we did also some things there. We're not proud of that, but it has to be done. Yeah. Other than that, options are there, and
there is some transferability of technologies in some areas.
Definitely.
Great. So we're going to go a little bit more into some of this discussion focusing on the energy materials, and I think we have a lot of questions on integration. That I think the idea that was open question by Michael, how we can really go through all these difficulties in that area. I think we're going to address that more. I want to forward the more questions on the Commission side. I think one of the things I know Francesco is working hard to basically understand the needs for acceleration in general, and also how emergent such a thing is in terms of the social aspects of it, as well as the long-term economic value. So accelerated material discovery might not be a hot topic as it is, but I think the impact of that is definitely worth of discussion and expansion in that sense. So maybe we can go into two questions at the same time, these two, from your perspective of the innovative pathway and the cycle of the materials that is of the focus for the commercializations, how it's going to come into play in your activity.
Yeah, I mean, from the side of the Commission, as first recently, but in my opinion, the good news is the fact that since 1 month and a half, the Net Zero Industry Act and then the Critical Raw Materials Act has put a little of boost in the side of the advanced materials for the Commission. That means the Commission has recognized also recently, it has been done this AMI 2030, that is Advanced Materials Initiative. And this is something like an initiative that tries really to group all the kind of materials company, including also the chemicals, based on the fact that as you said, Kurosh, there is a need to accelerate the development because, I mean, it's not the, I mean, I have to admit that also in the commission now a lot of people is no more speaking about energy transition, but materials availability for the energy transition. That means without materials, we know that we can go from one dependence on the Russian gas to the dependence on the refined materials from China for the energy. So there is a strong, I would say, policy attention nowadays. It's still at the beginning. And so this means that, in my opinion, there is a possibility to push some topics. Today with Kurosh, we were looking at in the last 2023 work program, there are 3 calls somehow linked to the use of computational. So computational design. And so, for example, in terms of my advice to your community is to push strong in the direction of the policymakers. So just to make them aware of the potentialities of acceleration platforms to make, once again, more available the advanced materials. I also think that another aspect really important that is when we look at the multi-level or multi-scale approach, that means developing the material since day one, looking at the synthesis side in terms of reactors and of the application side. I really believe that the capability to make the synthesis and to immediately start looking at its potential, let me say, application, how they work in the final application is really relevant, once again, to accelerate these kind of things. And on the side of how we work, I think, I don't know if Jens was saying before, when he said that there is a strong difficulty in exchanging the data. I don't know if he feels the same, but with a lot of projects where I work, I feel that they are in a way doing the same stuff. So many times also the same experiment without knowing, obviously, what the other ones are doing. So also in this sense, the capability to share data. I mean, nowadays we keep on sharing data through the papers, or the conferences. That is, I think there can be also some other kind of sharing the data in a quicker way to accelerate the development. And last but not least, in my opinion, what is really relevant nowadays is to combine the data that we are getting at the lab scale immediately with the industry needs. That means some type of conversion of companies, of chemical companies, toward the development and the scaling up of new materials can be possible. But for sure, at least I am Italian, I see in Italy that there is quite a strong distance between the chemical labs and the real chemical companies. That means, when I say real, I mean the scaling up or where they produce the commodities of chemicals. So also on this side, the capability from companies such as the one we have listened today, the capability to show the potential applications of materials acceleration platform is possible, not only at the lab phase, but also at the industrial phase. I don't know how much money the Commission can put on this side. Frankly speaking, I think no money, because this is an industrial activity. So the Commission invests in R&D. But in a way, I think that starting from the best practice to invest in one application with one company or one big company, then it can be easy to show the advantages also to the other ones.
Great. Yeah, so I'm going to build on that, back to Michael again.
I'd like to give him a question.
Yes, please.
You addressed an issue that is interesting for me. Scientists receive their renommee by publishing papers, and you had the impression that several scientists are working on the same topic. I have the same impression. Yeah. So, but when you want to change that, you have to find a solution for a collaboration of scientists. And a general agreement that working together is beneficial for everyone, and that the renommee then comes from that, and that's not from the published papers. I think the system itself is the fault in here. What is your thought about that?
Yeah, I can give you the bad example, and I mean, it's what you said. It's more or less 10 years I'm working on with different kind of really multidisciplinary scientists. And the bad example is now, once again, not breakthrough innovation, but in EIC, we work grouping the projects, calling this group of vertical common projects portfolios. And in a way, when they get the money from us, certain kind of projects, they are obliged to sign an agreement where it said that we will tell them eventually what to do, and they have to discuss. Normally, the commission gives the money and they do not enter in the details of your activities, okay? So here in EIC, we can enter in the details, okay? And we can do exactly what you said. I mean, we oblige the projects to work together, okay? Yeah, but this is maybe even the nice part, but the bad part is the first meeting I had, I was really astonished because, I mean, I was speaking with great scientists, and the first thing that they told me, yes, Francesco, but we need an NDA to discuss with the colleagues. So I said, come on, guys, I do not believe you are a TRL1. That means you are still as the atomic structure, and you want to sign an NDA. How can we work 4 years together? If the first day, the first thing you ask me is an NDA. So then, you know, you relax the situation. I'm used to discuss a lot. And so I tried to say, okay, come on, an NDA, okay. An NDA normally is done by A and B. In front of the table, we are 35. How can we do this? Do you want to call the 35 lawyers of 35 research centers of Europe? So you make the Jülich speaking with the Cambridge University, with the Bologna, and you make 33 lawyers. And so the good news is that after 6 months, I relax the situation, and now they start speaking. But I don't know if this is the good solution to your problem, okay? That is the real problem. So in conclusion, my experience is you can try in a way to drive the people, but first you have to get let me say, the authority. You cannot say, nevertheless, you are the commission. You cannot jump in a room and say, you do what I want because I'm giving you the money. This will not work. In a way, you have to convince them, to show them that it can work better if they work together, but for sure it is not easy. And I mean, we did only this after 6 months. I will give you answers in 2-3 years because this will be the time to understand.
Yeah. Okay, so we discussed that a bit. Jens, if you have any.
Yeah, I would like to comment maybe. So my perception of the science world is not that that too many people are doing exactly the same thing. I think that usually everyone has certain capabilities and certain pieces of know-how, certain pieces of specialized equipment, and they work on similar types of problems. Of course, in my sector right now, the perovskites are a very hot subject, but it's also an extremely broad subject. So there's plenty of room to do different things. But then there's also a tendency, I see a different problem with the publishing process and the way we receive merit, and that is that we really only publish the success stories. And we rarely publish the other things, but we learn from the other things. So experience, it's actually something my father always said, experience is the sum of all mistakes that you've made. And that's something that we really have a challenge every day in our laboratories. Because it starts when a PhD student leaves, and with him leaves a certain know-how of certain things, and the next PhD student, which we sometimes don't immediately have the funding for, he needs to relearn all of this. So this is really a bigger problem for me, is how do we capture all this knowledge that we tend to lose all the time, and that we also do not tend to exchange ever. So I think there must be a much larger pool out there of data that we share. What we find from the automation of our experiments, and especially from the automation of collection of data, is that we have much more complete data sets than we ever had. And now we are starting just for a subset of all the things that we are doing. And this is a subset where we really don't have too much manual interaction, but only the DOEs by the students or scientists. But for everything that is done automatically, we have complete data sets. They are well-structured data sets, and we can go into these data sets, and now we can really start to do transfer learning. We can say things, oh, this stuff worked pretty well in the past, so it's probably going to work reasonably well with this new material, and we can transfer all of this. And I think we need to find ways to leverage this much more, and leverage it across the cell size of individual research units, Bring it for, I mean, Jülich has 85 research units, so bring it to that level and bring it across centers and across Europe. And this is something that where we need to find solutions.
So I'm going to start this topic a little bit because that comes back. So Michael, I know you have been on the call for some time, my apologies. If we can also respond to and address these two questions as well as anything else you have in what we discussed. So we move forward to a little bit more details of the energy materials and the difficulties there. Mike?
Sorry, Courage, do you mean me?
Sorry, we have many Michaels.
Sorry, but I think it was already talked about very well. I have my hand raised because I want to add to this point. It's always, I think it's very important that the publishing culture needs to somehow change, or we can find a new way of publishing no results. I think we talked about a lot of this through our partners, and also throughout my times in, I guess, in postdoc and PhDs, that nobody ever talks about what doesn't work. But then there are people that's working on something that's not working. So there's always, if one can, it's not necessarily we need a lot of exchange or working together, but then if there's a systematic way people communicate what doesn't work, then we will be able to have a better path forward. I think right now we're only publishing what works, and then there's a lot of researchers that's working on the same thing that's not working, or they try to find a different angle that's has already been tried before, but it doesn't work, so it's not published, so nobody knows about this. I think it's a quite important point, but then I think this takes a lot of change, I think, on the scientific level to exchange these kind of data.
Thank you, Michael. Good. So we're going to give in the next questions, like after, I'm going to give some time that we have some questions online and all that. Is it related to the same topic?
I just wanted
Yes,
to make one comment to that. In material science, yes, we publish what works, and no, we rarely manage to reproduce the things that work in a different laboratory and from a paper that has been published out there. This is also part of the truth. And at least with our automated machines, we can reproduce, I mean, and this even hits us in our own labs because there are hidden parameters which we don't control and we don't even know about. And at least this reproducibility we achieve now with these pieces of equipment, and we have at least a reasonable hope that we could transfer this to other laboratories as well.
Well, that's great. I think this is the topic of conversation. We come back to the question, hold on to that. It goes a little bit sideways in terms of our focus on industrial acceleration of this, but it's an extremely important topic, and that's relevant to the acceleration. Without really looking into how we practice it today, I think acceleration is not going to help if that practice is not helping as we do it right now, regardless whether it's accelerated or not. So I'm going to go a little bit more into topics of the energy materials, and I want to talk to our core sort of, I call what you do in Zinsser as well as HDE is more agnostic approach to a lot of different fields. I'm assuming your equipment is adjustable to a lot of different fields, as you mentioned. So focusing on the energy materials as a focus. So we hear a lot about the energy transition, the emergency of that change that has to come 2035, 2030, whatever Commission is putting as a deadline, of course, and we want to get to that. So how much in terms of your technologies, and as I mentioned, it seems to be more adaptable because you can adapt it to a lot of different areas with some adjustment, with some work. What opportunity you see really on the energy materials specifically? I know Florian talked about these two topics, but I want to see really in a perspective of the business or market share that you want to get into. Is that an area that you think it's going to fly really hugely and there's a huge investment that's to be done, or is it something that you sort of seeing sort of hand in, foot out kind of involvement into it and see how that emerges?
Shall I?
Yes, please.
Yeah, so I have actually, I mean, we don't need to talk about batteries. I actually would say that's just huge enough. For the electrolysis part, I would say I have great hopes there as well. I mean, if one looks at the net zero demand, what we need, if one looks at what is announced already, and if one looks at where we are at the moment, there are huge gaps between these three levels. So it's a lot to do actually. And yeah, I come from the, before I went into this area, I came from the refinery. So my expectation is this area will be at least as big as what we have at HD for refinery. So, but one point I would like to say, this public funding, I think that as I see it right now with these three gaps, net zero announced at the moment, so, right now, I think this public funding is actually what we see is actually quite important because it kind of gives a kickstart. Since the market is not that broad yet, there need to be some risk mitigation by using this public funding. That's what we see from our customers. Without that, I think it would be more difficult. Actually, I had the same topic with biomass, let's say 5-10 years ago, where people said, why are you doing that? It's waste of money, waste of hydrogen. Nowadays, no refinery project without biomass or plastic anymore. And I think it will be the same, but we will have to see. Yeah.
You're taking a close eye into it, but you see how it emerges as well.
Yeah.
Okay. Maybe same questions to Zinser, Michael, please. How do you see energy materials as a big opportunity?
So I see it as a big opportunity for us. Our routine is that we are not employing for grants from the state or the European Union. We hunt for projects directly with scientists and hand over the responsibility for granting for establishing grants with the state to them, and only if they are going through, then we'll proceed with the project. What I see in general is, this is my humble point of view, it takes some time. And therefore the projects are lying dormant for a year, half a year, maybe sometimes longer. And if those applying process would be faster, I would have the impression that general advancement in the area would be better. So that is.
So from perspective of purely from a sales perspective, how do you evaluate opportunities in new areas that you want to, or sort of emerging? Is there more, what factors really involve that you feedback to your team or your organization that this is an area that, and or change the question, what needs to be done, and you have to see that it becomes important area of the activity for you to move forward?
So what I see is, I think the return of investment is most crucial, and investment here is like what could the scientists gain by advancement in the lab automation? Meaning, normally we will the scientists would calculate the amount of man hours that would be saved by the corresponding automation, and that is what drives indeed the need for automation. And so there are two ways: either employ cheaper employees. That's not the case in Europe. The other thing would be to employ cheaper automation and to have a higher standardization in automation and an interchangeability of parts there. That means also that spare parts, parts that are built should be more standardized and widely used. And that is, let's say, with the inhomogeneity of the market, a problem, and especially nowadays after the COVID crisis, when we still have the problem to receive hardware parts because there are chips in there, parts that are not widely available anymore. For instance, we receive from suppliers order confirmations which have ridiculous order confirmation dates, like 2049 and so on. It's still the case, and if, for instance, general production would be more based in Europe, or at least the western part of the world, that would help.
Yeah, I want to sure we get that. I want to get to that elaboration on the ROI a little bit, and when we get into specific equipment. So, Florian, please.
Just one addition to the question: why do we think there is something, especially with respect to electrolysis? We are focusing and looking into these areas because there is something going on also with our customer base. Actually, it's our classical customers, like refinery customers, suddenly talk with us about green hydrogen. They are restructuring their research departments and bring up new topics. That's actually what we also see. And there, of course, we have to be very aware of that. And yeah,
great. So I want to finish that questions with the Commission position in general into the energy transition. You discussed a little bit that materials acceleration and specifically energy materials acceleration from your own personal view might be, or the discussions, is that seen the same way as in terms of the targets that we are looking into, Francesco, in terms of the energy transition? Is the role of materials as well understood, and the acceleration that we have to get into, in 7 years, would that well sort of understood, or what do we have to do basically to make that message as clear as possible into the policy?
That's a very difficult question. I mean, I think that the policymakers, they do their job and they put targets. I don't believe in the targets, okay? I mean, we see, I mean, it's 20 years we're speaking about the COP 1.5 degree. If we look at the real numbers, I think that unfortunately, we are not changing enough our life, all of us. I mean, we continue traveling a lot with airplanes. We look at CO2. I'm one of the guilty of this thing. So on my side, I don't want to give the guilt or to make complaints with the policymakers. I only think that as a scientific community, we need to provide them in the best way the data to make a data-driven policy, okay? That's on one side. On the other side, I mean, I think that unfortunately, the disaster of the Ukraine war has for sure given to the citizens the new eye on the strong not reliability of our energy system. So we are strongly relying and depending on gas. And so the new era of materials for energy for the renewables, I hope it will be different since day one. So the only thing I can say is that, in my opinion, there is enough high level from the science world acknowledgement, but not yet enough at the social part. That's my gut feeling. In terms of Commission, I have to admit that there are good examples. If we look at the battery, the Commission has been able to invest, and it is investing a lot of money in batteries, from basic science up to the manufacturing facility. We don't have to forget that Northvolt received the loans of 3 billion euros. I spoke to 1 hour, I think, with the guys that developed it from the Commission and from the EIB, the 3 billion loan, and it's not easy to give to a single company in the Europe market 3 billion loans from taxpayers' money. It's not easy. It's maybe difficult enough as to develop a new material. So I think that the combination of the financial instruments and the science can enable new manufacturing facility of also of materials. And for sure, something that happened, I was reading a few days ago, that the amount of money that Europe, and in particular US, has given to materials in the last 30 years has been much smaller than what is being given from 60 to 90s, in particular in the refineries. There, Europe and US were in the leading. Now, in terms of refining materials from mines to providing the materials, China has done the big step. Nowadays, the Chinese are able to refine all or most of all the materials. They are not mining, they are refining.
Right.
And
so I want to get into exactly that to the next question. So I want to stop here, ask Angela if there is anything online to make sure that it's interactive enough as much as we can keep it that way. Is there any questions to the topic we discussed or anything you want to bring up? Kieran?
Not anything from our side at this point, and nothing has come up online, so you can continue on.
So we come back to that again. Did you change the questions? It's changing, so we can look at the second question and then third one would happen. I want to take one or two questions from audience here, please.
Yeah, I have one question to your comment, Dr. Haupt. I think you said that let's say much of the data that is funded is not really let's say reproducible, and that automation improves this reproducibility, at least from your experience. So would you see that the human as the main source of reproducibility? And does that mean, so what does that mean for, let's say, future experiments and also future, let's say, PhD systems, because these are doing a lot of the work. So do we have to take out all the PhDs from the loop?
No, that's not what I'm saying. But there are many things that are not well documented and not well communicated, and that are extremely hard to capture even in carefully written protocols. And this is a challenge. We just need to be aware of that. And we have this happening in our labs where people say, oh, you use chloroform and this polymer, and then you make your solution, and then one day somebody decides, well, we have a bottle of chloroform in the glove box and we have one outside, and if I use the one that's outside, I don't need to bring it in and out, and can save myself a lot of the process. And following that, we have a couple of weeks where our performance drops and nobody's figuring it out. So and these things happen. They're quite real. There are certain things where we have processes that are heavily manual, and just take the process of pipetting a solution. There's a written standard out there that you can buy for money, and then you can read it. I think it's about 20 pages long of how you actually have to do pipetting, and if you do it correctly, it is very reproducible. However, I don't know anybody that's read this. I don't know anybody that is actually doing it. And it turns out that, it's important whether you hold the pipette at an angle, whether you hold it like this. We recently did an experiment where we went through all the parameters of pipetting that we can control with our automated pipetting robots, just to see which ones are relevant. And there was one parameter which was quite relevant to this particular process, which we've never focused on, which is simply the distance between the tip and the substrate that we deposit things on, because stuff happens in the while we're depositing this drop. So this is what I'm saying. It's for a system where I have a certain amount of parameters that I'm setting. I'm limiting the amount of free parameters that are out there. And in this system, I can reproduce what I'm doing very well. There are many other free parameters out there, especially with the human body is quite good at, we have a lot of joints, many degrees of freedom. And that's why we're very good at doing many different things, and we're very flexible about changing things. So, if we discover that opening a bottle is better doing it this way rather than doing it this way, then we simply use our hands and do this. But if I wanted to have a piece of automated equipment do this, then I need to teach it like this. I need to design everything. There's a certain cycle that I need to bring in. So this is the thing that we somehow need to balance. The people give us the flexibility of doing things. Robots and robotic systems, automated systems can give us the reproducibility, and we need to find the way of leveraging this.
Yeah, thank you. Is any quick comments?
As an automation supplier, I would also add something. So I presume that you had the impression that if you would have the same equipment as his in your lab, and you would transfer your application back up to his lab, would you have the same results? I don't think so. There is mechanical hysteresis, first of all, in the mechanical components that you use. That is not really recorded in log files. This has to be like fine-tuned, and the application specialist that sets up the robots should have a look at that and compare this on different setups. And then you have a fine chance with the given accuracies or CVs that you will have the same, or at least approximately the same pipetting results. So there is also.
But that has to be part of the documentation.
And
also, it's good by statistical errors must be reported as well. The question is, where is the reproducibility loss? Right? So, of course, when you look at the publications, you don't look at the more data. They are processing data. And I think in the processing, that's where a lot of the getting stuck, because then there's a bias that is into, for some say, this certain property, I don't know, for your models to compare with, let's say, what range of the data you use to do a fitting, for instance, right? So those issues come to, and there's always a bias in that. So, and we never get access to the raw data. So, or that's actually very difficult to get by.
Yeah. Great. So I'm going to move on to the next topic. A little bit more clear view on what was discussed a little bit on circularity, supply chain, and some other sort of boundaries that we have to work on materials now, which are more important today than what it was 10 years ago or 20 years ago. So, so looking at the energy materials in general, and transitioning that we're going to have to the greener source of materials and components. So fundamental research is basically not able to generate any insights on economic value, obviously, right? So we have to look at a lot of these things in terms of, and it's not inherently involved into that process that conventionally we have looked at. We have not looked at circularity as part of the research project. Has never been as part of the sort of blueprint of research the way you do it. Commission, as you mentioned, there are some mandates in a lot of projects that is coming that has to have the aspects of the circularity, economic viability, and all that. So the question is that how do we really adopt this with all these aspects? Who is really, and do we really know these aspects to include it? Do we have to learn how to address these areas and all that, and how we can basically. I want to start with Jens in that topic, because you work on a material which is, of course, is highest important as one of the most sort of elements of the transition. And when you look at the fundamental research that has been done, of course, there are weaknesses in addressing those aspects of circularities. Do you agree that it's still we have to pay for it and we have to look at it? And do you think all these elements that are adding into the equations make the actual research and science sort of diluted? And we have to focus on areas of circularity and supply chain where the actual science that goes behind of the development will become less and less important. So basically, how do we address those things in your process? And do you think we have to have a balance of still science and also the economic and socio-economic values, including circularity and supply chain?
Absolutely. So I have a strong industrial background, and Christoph Brabitz is our director as well. So we always focus on these things, and it's actually quite funny that you bring it up, because one of my team leaders just recently won an ERC grant for developing cradle-to-cradle photovoltaics technology, because we believe so. Even in photovoltaics, we're going to have a material supply problem. Just the amount of silver that we need, the aluminum framing that we need, the glass that we need. If we simply scale the technology that we have today, we're not gonna be able to get all these all of this, and that's why we want to, or with these emerging PV technologies that we develop from scratch, we actually have the chance of really recycling every part of it. But if you want to do that, you really need to rethink the whole system. You can't just change one part of it, because nowadays, I mean, a silicon photovoltaic module is more or less bulletproof, and it's made to be like that. And your chances of recycling it are simply by more or less grinding it up and trying to recover the silver, and the rest you do better, turn into better landfill. But you really need to rethink the whole concept of how can you actually separate layers from each other. This is something that we're going to explore, but this is really, really new. And I think there are many other aspects or many other technologies that we really need to bring it into as well. But I fully hold the opinion that we need to sort of have this global thinking, and we need to identify these future shortcomings when we scale things.
Right. So you think we know how to do it in some areas. I want to hear from others if that's really the case in all aspects of other energy materials, batteries, electrolysis, and all that. Do we have understanding how to address these other aspects, or do we need to still research to understand those, please?
Yeah, I think a battery is a good example where people more and more realize that recycling needs to be part of it. It's so big already that it's really being, I mean, you see BASF, Umicore, all of them building up recycling capacity. So I think it's really going into that direction. And I think it was said already, and I think plastic recycling is a good example where the plastic recyclers have this initiative designed for recycling. And I think you said it already, that needs to be implemented. So not start thinking about recycling when you have the dead product, but actually before you design the product. And what the plastics do, say, one thing is you could think about the monomers, how to make different polymers, but there's also this part where you actually can, you design your material and you look at all the components, and then you rank them according to recyclability. And that's actually a very simple way. And there you start already for the design. You think, where are the critical steps and can you improve it? And I think that will come. And battery is a very good example where I think this starts.
So same question. I think the aspects that was discussed is that do we focus on existing materials and try to find a better way to recycle and address that circularity, or all the way we're coming to a new materials that are more acceptable in that? Which way really is the best way and more economic? Might not be an immediate answer to that, but I want either of you, if you can elaborate on that as well.
Yeah, if we look at the economic point of view, it is written, there are many studies that shows that when a materials is increasingly in a steep way it's used, for example, in these days, in these years, lithium, the recycling cannot be the solution. I mean, it is part of the solution, but it is not the solution with the capital letter, because the amount of time before we will have lithium enough to be recycled, it's not one day, because one battery luckily doesn't last only one day. And so we need for sure to optimize and to look for new materials. Another thing is the cradle to cradle approach is good, but normally there are three approaches. That means once the first and most difficult one is life cycle thinking. That means when we design a product, we already design it for circularity since day one. And so we make a battery that is already disassemblable. We already know how to divide it, the same for the photovoltaics. If we do the second approach, that is we start from something that has not been designed to be recycled or to be circularity, it is much, much more difficult, and it depends on the product. Yeah. Then there is in between, that is the market and the policymaker can oblige you to make something, as you were saying, with a certain degree and type of recyclability. This is where the policymakers are working, and where my colleagues in this year, I think they will start from some markets where it is more easy. That one is the packaging and the other one it is the textiles, because the customers are maybe and hopefully more prone to pay something To conclude, the policy aspect in the side of circularity, in my opinion, will have a very important role, as it happened for other kind of development, let me say, more green technology. A few days ago, I was listening to some green steel scientists that were saying that Europe is much more developed now in green steel, more than US, because in Europe there is a emission trading system that is a policy that in a way obliges the big emitters of CO2 to, in a way, change their process, or they will have to pay. So I would say that in circularity, policy is as well as important as the technology and the new development of
So
materials.
just one question, yes or no. Do you think adding these things into the mix decelerate the acceleration we're talking? Is it going to slow down the process of acceleration, or do you think it's something that can happen hand to hand with this? Anyone?
I don't think it'll slow things down. I think what we need to do and what we need to get used to is something that we call multi-objective optimization. And there's the Edisonian approach. So we optimize one thing, and then we optimize the next, and we optimize the third. So in photovoltaics, what is typical is you optimize efficiency. Then you optimize after that, you say, oh, it needs to last for longer than 5 minutes. So you optimize stability, and then you discover, ooh, all these solvents and this stuff we'll never be able to use in production. So now we need to optimize for production, and this is what we're trying to actually do immediately with these automated lines that we have. And in a sense, this circularity then is another objective that we need to add into the mix in order to take it into an early account.
Can be addressed. Well, that's great. So I want to move on to formal questions, and then I get back to audience online and here as well. So Mike from ECHO, this is more towards what you do, of course, here, but then I want to get back to equipment manufacturing as well. So when we are looking at the integration parts, there's an integration aspects of the automation that you are building. You're building the equipments that basically handle materials, but you also have to add characterization. So there's an integration has to happen on the equipment side. There's also integration has to happen on the material side. That the material is developed regardless of the way it's developed. It has to go to different scale, including to electrode, and then electrode has to go to a device, and then it has to function as we discussed earlier. So Mike, in your process, where do you think on the integration of materials from what you get as is or you develop internally into the device? So what are the ways that you think the acceleration can happen? And where do you think integration sort of bottlenecks and roadblocks are as far as the material itself or type of analysis that you do internally as a company?
Thank you for the question. I think integration of material it's a good question because we in our company we're almost at the last step before we talk to the customers, so we're never at the top. I think it would be much easier if any innovation or acceleration comes from the top of the supply chain. We always get questions from suppliers says, oh, we have something new, do you want to try? And then there's always risk in steps. They have to make the risk in making something new, discovering something new, and then try to find ways to scale this up so that it will be acceptable for their customers, which is us, which is me, EKPO. Then at EKPO, we need to accept the risk that, okay, we'll take this experimental product and then we'll put it in the process, and hopefully it works. If it doesn't work, then there's a risk that it doesn't work. There's also a risk that it works very well, but then it cannot be scaled up to a proportional volume, or it works very well, but it's very expensive. So there's always different levels of risk that one needs to take in account of for integration of different levels of technology readiness levels. But
is there any acceleration required into that process of assessment, or do you think what it's done into your protocols of certain properties of the materials that you get is enough to reject or evaluate those new?
Yes, we have some modeling. Essentially, what Professor Eichling is doing, and a lot of physical modeling on the materials level, and then we do a lot of testing. So we do systematic testing. So we always rely on testing results. We rely on a sensible design of acceleration stress test. So we don't use the stress test as an evaluation method. I'd say we don't use it as a evaluation method. We use the stress test as a comparison between the materials, so we can have a better understanding of what's being developed. And then, yeah, of course, so the acceleration comes from a systematic way of systemized testing. So it's always the same protocol, always the same procedure, and then all we do is swap in and out materials.
Yeah.
And then,
okay, great. So I want to turn that question to Michael's answer here in a different way, but they're sort of related. That when you look at building equipments that basically make this process of materials to device or cell, we are dealing with a little bit of different system that has to basically build into material properties and also do the cell sort of testing as well. So in terms of integrating of different components, in terms of the hardware components, that is a standard, as you just heard, there are some standard sort of procedures is used. To be industry acceptable testing, how do you think difficulties of building those testing into an automated process in your line that applies to the energy materials need that has to go a bit beyond the scale of the material characterization itself? Do you have to resize characterization? Do you have to redesign it? Or do you have to go to the OEMs to do it for you?
So regarding materials, we would concentrate on liquids that would be easy to process in an automation. So therefore, consulting would mean that more viscous ones could be avoided, or if an alternative could be used for the automation approach. That is one alternative. Regarding integration parts that are not automatable available. So there are certain, let's say, third-party instruments that foresee already the capability for a automated integration possibility with an API interface to talk to. You know what I mean? These are then more easy to integrate than fully manual versions. Obviously, when you hunt for an implementation of an automation process, then the first mentioned instrument types are easier to implement, and the later mentioned ones are more complicated, and you have to search for also other solutions. Easy and nice to understand example is, for instance, the implementation of a centrifuge. There are, let's say, 4 or 5 models available that are easy to implement. Then there are benchtop centrifuges available, but they don't have a communication protocol at all, and how to load them. But that could be avoided by, let's say, collaborative multi-axis robots which have the capability to identify not interfaces optically, and therefore they could be used. So that might be an answer.
Okay. Okay, so basically you're finding a solution to basically.
That's engineering.
So back to you with the same question, Jens and Florian. You have done it for many years. I think you have gone through sort of up and down of this integration. Even to my opinion, your system could be simpler or more difficult than a battery and electrolysis, depending how you look at it. And I think that's a good insight if you can add. How was it difficult to basically go? And then I want to hear if that it's a lesson learned that can be also adopted to
I can start as, I mean, we're not professional equipment builders, we're scientists, material scientists, but we just simply started doing this. But the API is the magic word. Finding a piece of equipment with a well-documented interface, when you have it, it's great, and you're really willing to pay for it then as well. And that's really a problem because we need a lot of specialized equipment in the scientific market. And the typical way these pieces of equipment come is with a USB port and a laptop with a custom software that you plug into, and USB is terrible. So we always we try to find a piece of equipment that at least have a TCP/IP port. And then there's usually an unwillingness of, and oftentimes at least there's an unwillingness of the providers to share with us the communication protocols. So we needed to get good at spying out interfaces as well. So there are many hurdles that need to be overcome, and we're really, from my point of view, there's no need to do this, but everybody tries to sort of protect their little share of the market, and it's hard work to get around this.
I think some changes in that industry has to happen really as one of the drivers. So on the same question to Florian, of course, we discussed the adoption of new. So how do you ensure basically test protocols that was mentioned with Michael, for example, if in electrolysis that you adopt that to make it industry acceptable? Are you building your own equipment? Do you think the OEMs that you work with, like Metron and similar, are ready for that integration, or do you think at some point you really have to get insight into building some of this characterization yourself?
Yeah, but first of all, we are the system integrator, so we are taking the pieces that we need to make it to a working system, and then of course it's about benchmarking. So it's simple, hardworking experimentation to see if it works. And I said it before. It's the most important thing, if it's classical areas or the new areas, is that you have proper benchmarks and then have proper protocols that you have to develop. And I think that's a weak point actually in electrocatalysis. That's we are on the way to standard protocols, but I think there's still quite some deviation. And that's just what we have to do there. And I follow exactly Mike from ECPO. There is in production, there is a huge need for already for materials qualification when we are really in the market. And again, one can look to the old industries. They're heavily using high throughput experimentation, for example, in the refinery to qualify their feedstocks, their catalysts. And I would say an electrochemical cell is more complex than a refinery catalyst. So there is even more parameters, even more components that need to be checked. And as Mike said, systematically compared. And
so the idea is that it's really on the system integration side, OEMs also have to adopt in terms of having standard APIs, be flexible into those adoptions as well.
Yeah, and also some basic things. For example, we are going up, and we had it the surface as the area. We're going up in area, so we also need equipment that can follow with the current. 20 ampere booster is not enough, for example. We want more, and so on. So it's very basic things where we stretch the limits and where they have to follow.
Okay, great. So I'm going to have some questions from audience here, and the third question is already up, and the audience will look at that at the end. And I have one important sort of topic to discuss. We are at GCMAC, German Canadian, focusing on this topic, and we're going to look at opportunities to basically, at least within this community, learn and adopt what we're talking all in terms of standards and things. So let's get some questions from online. If there is anything, Anjali. Anjali? No? Okay. Yes, please.
There we go. Garage.
Yes, please. Sorry.
Courage, there's one that we put in Slido, whatever it is. The question was, I better read it because I put it in there and I'll just read it. Okay. The first part of the question, when you were talking about circularity especially, is there anyone integrating LCA and TCA? So TCA being techno-economic analysis into our experimental planning and process development efforts. And then there's a follow-on after that because you really did address circularity. But what about the techno-economic analysis? Let's think back to a few comments about ROI. Any thoughts from the panel?
That's a good point. Yeah, I wanted to bring that up on the ROI of the equipment as well as the materials. Any input into that?
I mean, on the side of the LCA and TEA, there is the LCCA, that is the life cycle cost analysis. We speak about of acronyms. So yes, there is a way to integrate to see if the circularity can be based also on real economics. That's something that the scientist can do. There is the tool. The other way around is when you are obliged to do circularity anyway. That means if the policy tells you that you cannot use anymore one shot plastic, you have to change everything, and so you have to find your way to make it reasonable. But if the policy is obliging, and in certain materials it will happen in 2-3 years time, then you have to find your solution from the automation, from the facility, the manufacturing facility, and things like this.
Yeah. So to yes, is that a reasonable sort of optimization parameters that you can add, or that has to be something else?
We also do some techno-economic analyses, but usually techno-economic analysis is a tool for us to choose sort of a general direction, to determine, if we had such a material with these properties, how would it affect things? If we had the opportunity to put a perovskite topcell on silicon, what parameters or what properties must it have in order to make economic sense? And from that, we derive the large range goals, but we don't derive the input for the short range design of experiment, for example, that we do in order to optimize a certain system. So in that sense, they're two a little bit different tools. Yes.
Okay. Not into actual optimization process.
Yeah.
I hope that was enough as an answer.
Courage. I have one follow-on because I really appreciated that answer. It sounded to me like the TCA concepts are integrated at the screening stage, much like we would use computational predictions for materials to screen down from tens of thousands of options to some more obvious options. And I really like that answer. So thanks very much for raising that.
Okay, thank you, Mark. Is there any other questions on your side?
Not that I see here, thanks.
Okay, thank you. So we have one question from the audience here, please.
Yeah, I had a technical question earlier in the panel discussions how we were talking about how you can even more accelerate your closed loop system by assessing these descriptors that serve as predictors for this final performance. And switching over to Mr. Cooper, I was wondering if you could think about something similar in electrolysis systems where you can come up with some descriptors for electrolysis that could define or predict your final performance in an MEA or electrolysis, for example.
Yeah, that's clearly a topic, of course. I mean, we had a very long discussion on that topic. Hopefully we are successful to bring the steps of the material synthesis to the MEA, to the cell, and finding descriptors that are before you go the full way and can describe what you would expect electrochemically. So it is exactly the same story and exactly the same topic which we have. That means also here we saw the nice picture connecting modeling, characterization, and testing. These together and then create a huge amount of data which can be then used to really find these descriptors between electrochemical properties and physicochemical properties. Yeah, definitely.
Of course, it gets more complex depending on the system, but yeah, that's the same. So I want to finish with the ROI because I want to get into that point. These equipment's acceleration, when we talk about ROI from the perspective of the company that providing the equipments, is that more reflected on the labor cost and the usage, or is it more number of experiments? What is really the ROI you find in your perspective when you try to sell, to have a sell pitch, if you like? How do you really convince someone in a conventional lab to switch, if that's really one of the KPI you're looking at? Is that more labor cost or is it more easiness? Maybe you can specify a few of those.
For us, it's the other way around. So the scientists have to convince us that the automation makes sense, and how, as we are not the real expert in the field of expertise of the scientists, they have to explain us what.
You familiar with those at the start of the project, and do you keep your product to fulfill that requirements, or is it some flexibility has to be there too?
It depends. In the field of chemistry, this is definitely a different thing to my field of expertise. So I'm a microbiologist, geneticist. I have a background in biotech engineering, and therefore I can give good evaluation and hints how to operate a system on molecular biology basis, so mRNA basis, something like this. In the chemical department, I have to rely then on my knowledge in the let's say automation experience that I have, and just trust in the knowledge of the scientist that what he describes, what is important for the process, I can translate in technology.
Yeah. Okay, so I guess the answer is that the experts has to look into it, but it's driven by the customer in your case.
Sometimes.
Okay. Okay, so I want to get into a very general questions here beyond all the technicalities of the process we talked about. And we talked about the standardization, we talked about a lot of activities. To leverage a lot of these learnings that I think yesterday we had a discussion on what happens on the Canadian side, things that has started from lab and emergent, and certain sort of areas getting more mature in terms of understanding. There are areas that we talked today that are more complex and needs more adjustment into the descriptors, not known even as the conventional process, not to mention an accelerated process. Equipments are not necessarily the same format. So I want to start with Francesco on that. So we're looking for basically GCMAC as an entity that basically is trying to focus on, or as a sort of collaborative entity that is trying to get into leveraging all the learnings on this side and that side in Canada, and basically get all this happening. So what are the availabilities of this? Well, how do you think knowledge transfer can happen between two? Is there anything in Euro that we have to look into a bit more? And sort of what are the opportunities? And then I want to hear from also industry and companies if that process makes sense, and what are the requirements should be there so that this can be leveraged.
On the practical side, as far as I know, in terms of possibilities of collaboration, it should be signed end of June, or maybe also before, the agreement between Canada and European Commission. So from 2024, Canadian entities will become as an associate partner to Horizon Europe. So there will be the possibility to apply only to Pillar 2, as far as I read on the papers. And so that's the first opportunity. And in terms of other kind of spillovers, I think that what is the good opportunity sometimes is, I know that it is really time consuming, but unfortunately it works, as far as I know, in this way, to look at all the calls that are present, because a lot of calls are are not well known. I always suggest that, I mean, in the research centers as well as in the companies making R&D, there is someone that has to study the codes to look for example, in terms of manufacturing facility, the European Commission since some years is funding via the Innovation Fund the possibility to get money to make the pilot plants, but also the manufacturing pilot plants in 4 topics. That is hydrogen economy, CCU or CCS, renewable energy sources and hard-to-abate industries. So this is something that can be done and you can get the money out of this in terms of opportunities. And last but not least, what is nowadays a lot of attention is done in this kind of public-private partnership. So I am pretty sure that is under discussion in European Commission. I don't know. I think it will be starting from 2027, but there is this partnership on discussion to set up a partnership on advanced materials. And so this could be something where the GCMAC could try to bridge and to make lobby. I don't know if you are familiar, but these PPP there are different levels of money coming from private, given from the Commission, and these kind of things, as far as I know, there is the willingness to push in this direction.
Okay, great. So in terms of the SMEs that are, or industries that are basically engaged in these things on the Canadian side and the possibilities that we have in this panel, huge activities on the hydrogen electrolysis, let's say in Canada, in terms of protocols, in terms of the requirements for new equipment. What do you think the sort of our activity and funding and possibility would help, and in what way? Or what would be your desired way of collaborating and having access to those, either Michael or you? So.
Yeah, okay, I can start. Yeah, so I mean, on my wish list, or first of all, I think GCMAC is well equipped to accelerate or to facilitate this topic of AI supported experimentation. And on my personal wish list, is actually really to drive this topic further, to see what there is to gain, because I think it's still to be proven that this actually adds value in some areas, in some not, but in other areas. And from my point of view there, I think this public funding is important to promote these activities, because it's kind of, for us, a risk mitigation. We want to try something where we don't know if there's a return on invest. And at the same time, it facilitates the cooperation of institutes and also companies, because there needs to be also institutes need investment, need PhDs and so on. So that's my point of view on that.
So on AI,
exactly.
So we focus on, you think that's a good. Michael, do you think on equipments, is there anything that you think you can lead some activities there or some?
I think the biggest support could be really with the AI, and before that we should discuss how the raw data could be exported from analysis instruments, and then obviously AI comes in for identifying new experiment sets, parameters, and this step is already large enough that.
So you think in your process, software, data, hardware integration is still a topic of
definitely
difficulties of it. And Jens, what other things do you think you can suggest as ways that we can leverage the knowledge on both sides to accelerate the effort?
First of all, I agree with everything that has been said. I think what is probably also important is the step from data to semantically linked data ontologies. So I think that's something that needs to be driven on all ends. And one thing that is on my wish list, so it's for us, it's very difficult to create these platforms that are capable of solving large sets of almost rather generic problems. So we really had to piecemeal these platforms together, because we've never received any funding for creating such a platform or for the engineering that goes into it. So, and that's a real problem. So you always had to define some sort of very specific problem that you get to, and then you buy a component and you plug them all together. But we could never actually go into it with a vision of, okay, we're going to create a platform that is capable of solving many problems, and we're going to do this in a very good way. And there's a real discrepancy there because the funding really doesn't allow us to do this.
A lot of message for you, Francesca.
But this is something that, as far as I know, has changed since Horizon 2020. The Commission decided not to fund a lot of equipment. I don't know why, but that's so they fund more other kind of expenses. Then there is this administrative rules that, frankly speaking, I do not understand. But this is what looks like when I look at the bills of the projects. That the money they ask, they cannot ask for equipment. I mean, they cannot ask a lot for equipment. Then there is also this amortization. Then there are all the parameters.
Yeah, but I mean, even if we had the idea that we're going to go into an EU project with sensor and with HDE, and we're going to create a centralized data system, and we're going to create certain pieces of equipment that actually generate data, do certain experiments, feed it into one place, are centrally controlled, can somehow communicate with each other. There's real work that goes into it. There's real development effort that goes into it, and there's a lot that goes into it, but I have no idea where we would get the funding for this, to be honest. And that's a true problem. And that's holding us back from actually developing a field like this.
Great. So I think that's we stop there. That's really a good wish list to put there and work on that for hopefully some outcome soon. While we're putting this result of those questions to the audience, I want to open it up again to any question from on the Canadian side or whoever is online.
I don't know. Oh, sorry. Go ahead, Robert. Oh, no, I don't know if we have any questions on this side.
There are some on the chat. This is Alicia Main here from Vancouver. I'm happy to read my chat question if that makes sense.
Oh, yes. Hi, Alicia. I thought you have your question yourself, but yeah, please go ahead with whatever you think.
Sure, I didn't sign up to Slido. I just put it onto the meeting chat, but thank you for the part of the discussion that I was joined for. It's just coming on 9 o'clock here in Vancouver. I really enjoyed the question as well about the life cycle analysis and the techno-economic analysis being integrated very early on into the research. Because if we're talking about accelerating materials discovery and adoption, we have to be considering all of those aspects really early on. And along a similar stream, there's many other pieces. We know that there's a huge gap between discovery and actual take-up in industry. And there's many pieces of research early on that can accelerate that entire period. So my question is, what are your plans for thinking about innovation management research? For example, technical economic matching, technical market matching, the need for complementary innovation, downstream process innovation requirement of a new material, value proposition in specific market applications. Have you been thinking about how to integrate that into the research stream?
You want to take that?
Maybe I could have commented before. I do it now. What we see is in the field of electrolysis, there is actually heavy discussions on techno-economic analysis because I think this topic of electrolysis or co-electrolysis or electrolyzing processes still needs to show that it can actually compete against or it always has to compete against the classical processes. And over the last years, we had discussions on developing electrochemical processes, and the very early stage always was like this: can we compete against the benchmark processes? And that's really a tough job, and it's not. Probably one also has to address it from a political regulation point of view to make the benchmarking processes also more comprehensive with respect to CO2 and so on. because what we see, the electrochemical processes really have a hard job to compete against the classical ones. And that's in the early stage before we start any research project. This goes up and down techno-economical assessments. Yeah.
But you mean, Florian, that in this way, once again, when you say that the comparison is not fair, it is because the traditional one is more CO2 emitting in this way.
Yes.
So in this way, as I said before, I think that on this side, the policy can make its role. As Alicia was saying, if in a way let me say it's not polite, but if we oblige everybody to make an LCA on a techno-economic analysis and to make out of it the valuation of the CO2, and if you make more than this, you pay, as it is now with the emission trading system, some good results we are getting back. But for sure, the lobby of cement and steel does not love it a lot. So that's something we have to consider.
Yeah. I think about, I have a lecture at sustainable chemistry at the university, and we looked at the ammonia synthesis process, and I was kind of horrified to see from the methane, it takes the hydrogen and the carbon is just released as CO2. It's a classic process. It's
95, it said 97% of the hydrogen nowadays is done like this. When everybody now, we call it gray because it is more polite, but we are exactly getting CO2 and throwing it away.
But that's a benchmark. So if the benchmark is not checked critically, the electrochemical have no chance.
It has to be within that benchmark.
Yeah, yes.
Did that conclude that question, Alicia, or do you have any other things to add?
No, that's an excellent discussion. Thank you. And I would just encourage you to think critically about what kind of research stream, whether that's some of the political questions and regulatory questions, or whether that's some of the valuing those different costs, and whether it's the strategy from getting from here to there that gets integrated into the research stream. And I know that means working with interdisciplinary scholars, but I encourage it.
Okay, appreciate that.
Courage.
Yes.
Yeah, if I could just throw in one comment. It's Mark Cosgris, Alicia. Thanks very much for the question. There's a couple of responses that came to mind and I think that are important. If you listen to the panelists and get their thoughts on this, the market's driving their activities. So GCMAC has this responsibility to work with industry and with the people in industry that have that market knowledge and market pull. The second thing is, of course, I've been involved with your activities in this area. And so I've got enough knowledge to be dangerous. And I guarantee you that we are thinking of it. We're looking on how we'll integrate it. And the research stream activity that we would do will come because of our awareness. And I think awareness is one of the biggest things that we're fighting right now to try and move all of this forward, acceleration forward, market impact and integration forward, all those things. So thanks for raising that. And I guarantee you we'll try and address it moving forward.
Sounds great. Thank you.
And we also have one more question online from Thomas. Thomas, did you want to ask your question directly, or I can also read it out? Thomas Axteller.
Yeah, just go ahead.
Okay, I'll read it. So the question is, will there be standards developed for the lab setups to make them interoperable, standard dimensions of equipment and samples, standard communication formats, and standard program setups?
I'd like to take that one.
Yes.
So regarding standard communication formats, I presume something like drivers and communication with third-party equipment is meant. So there is something like a SILA aggregation, but all the lab supplies are not participating really in that. So the theory goes as this, that once someone programmed the driver, everyone else could use it. Yeah, so, but that is not the reality. So the intention is there, a good intention, but not everyone uses it. So regarding standard dimensions,
equipment, I think this can't be done because let's say a spin coater has other dimensions as a spectrometer. So there's no way to standardize that. But for instance, for samples, there's already an agreement on the so-called SPS format. So meaning a leper that is 127.5 times 87.5 millimeters large in X and Z, X and Y dimension, which is usually a microliter plate, and that is widely used. So in lab automation. Other than that, vials are not harmonized at all. The standard program setup, I presume, is something that might be really interesting. You're using quite a lot of Hamilton equipment, some TCANs, I know that, one at least. But that's standalone.
Yeah, but it would be nice if you could exchange the product.
Absolutely, it would be very nice.
To Dinser machines and vice versa.
Yeah.
Reality, no. So there has to be some translation done in between, also the corresponding, let's say, liquid class. If this does ring a bell, are important and it can't really be translated. It would be up to the lab suppliers to organize themselves here. Reality, difficult.
All policymakers actually requiring certain things.
Yeah,
Like in the consumer market, you know, where in the future you have to make sure that things can be repaired.
Right.
So it is possible to implement such a thing, and it could really help accelerate a field, I think.
Great. So I'm going to the last question here, and then we're going to end up with closing the session, please.
Thank you very much. Just a quick observation and a question. The observation being it was a great 3 hours of conversation. However, human-to-human learning is incredibly inefficient. I think it's like 50 bits per second. So the last 3 hours, we managed to, I think, transfer 7% of a megabyte of data. But anyway, moving on from this, so there's the advantage of maps. Moving on from this, question directed at Francesco. What is your reading on the implications of the European Critical Raw Materials Act that was passed in March 2023 on the funding landscape moving forward, and whether you see materials acceleration playing a vital role? It's a home goal, but I think it needs stress too.
Yeah, okay. First, all the Critical Raw Materials Act is, I think, will be definitely, so to come back to your question, it will be defined completely, I think, within the end of the year. It is now under discussion with the member states. It is managed by the Ministry of the Commission, by the DG GROW. I attended informally one meeting with the member states, and each member state is giving also a kind of mapping of its resources. So to lead then the Commission to make a general evaluation of where the resources can be eventually exploited. As far as I know, but I am ignorant of this, what I understood from this meeting is that it will not be the money from the Commission, but each member state will be responsible for the critical raw materials. In terms of the impact of the acceleration platform, in my opinion, it is, let me say, obvious. If we want to develop new advanced materials alternative to the critical raw, we need to go in a way to accelerate. And the MAP, the materials acceleration platform, is one of the tools that I hope will be implemented. Up to now, I think that there is a lot of effort, as far as I know, in certain fields, not in all over the fields, and in certain kind, not only of fields, but also of companies with a certain mentality. I think that what is also now needed is to speak really with the top management of the big corporates to explain them the money advantage, because they only look at the money. So that's a way eventually to bring it to the high level of customers.
Thank you.
Was that good? Okay, thank you. So we're going to have this. Obviously, everybody's from R&D field. There's nothing surprising. All the industry participants are sitting here. So I think one of the things we try to understand is that the same thing with what the interests are. So obviously, the tops or the same level are in high throughputs, applying machine learning, data-driven approaches, advanced computational simulations and multi-scale modeling. So really, it's more about doing experiments or doing work that they do faster and better. And last question. It seems that data has been really a topic that as well as what was brought up here. In terms of growth tools and interdisciplinary collaboration. So future of materials innovation stays as an increased reliance on data driven. I think that's was brought up a lot here. We having more and more data. There's not much or enough is done in terms of utilizing it in specific application or industries. I think it makes some breakthroughs and potential for circular economy is not on the top, but it's one of the areas that was mentioned. We'll keep doing this kind of things in our future as well, and hopefully with a more diverse set. Okay, so let me thank all the panel members, presenters, as well as the panel members with the hardcore discussions that we had for 3 hours. I know has been tiring, and really appreciate your presence here and all your inputs. And I hope that it has been helpful as well as insightful for all the audience here and in Canada. And thank you very much for your presence. Thank you.